Perfect. All right. Thank you everyone for joining the second workshop in the IntelNova Solutions Data Science Workshop, first ever Data Science Workshop series. And we're very, very excited today to be presenting you Redman, who is going to talk about the intersection between data science and neurotechnology, which is a very, very niche I would say use field of data science and software solutions. But I would say it is a very cool field, and me personally, I'm very interested in it. And even if you're not an experienced neuroscientist, or even if you don't know much about brain science and anything like that, you can still see how cool data science or software solution is implemented in this field, and it can hopefully give you some ideas for your future projects. And I'm sure that this is going to inspire a lot of us in our own personal projects as well. And I'm personally very excited because Eden's walked me through his presentation, and there are a lot of very interesting projects that he's going to touch on. And he's actually turned some of his projects in his basically startup incubator into pretty successful startups. So we can also hear a little bit about his experience commercializing these projects. So yeah, everybody, without further ado, I will introduce you Redman.
Hello, everyone. That really raises expectations. Thank you. Yeah, I'm Eden. I guess I'm here representing myself, but just kind of doing a shout out to NeurAlbertaTech, which is the premier neurotech innovation network in Alberta. And yeah, glad to be here. This is one of my first forays into kind of introing to other people outside of neuro, outside of potentially academia, what it is that I do. So yeah, if there's confusion or questions at any point, feel free to just interrupt me and ask. But yeah, I'm going to talk about who I am, I guess what gives me any amount of authority on this topic. Then I'm going to go through some projects, specifically previous projects versus current projects. And then I'm going to be kind of hopping back and forth between the underlying mechanisms as far as tech, and a little bit about the brain and the signals that we get from the brain.
I have a question. Are you sharing your screen? I don't see your screen.
We don't. Oh, there we go. Yep. I clicked the wrong button. All right, so this is me. I have a few roles. I'm here talking to you today because a lot of what I do is data science related. And to that end, I'm the executive director of NeurAlbertaTech, or you can just call it NAT. And yeah, there we offer workshops and speaker series, competitions, yeah, and project support for pretty much any projects involving neurotech, basically the brain. So it's fairly all-encompassing. I'm actually in our new office space at the University of Alberta. So if you're ever around here, or that's where you're tuning in from, come check us out. Also the CEO of RemBRAINdt, and so that's, I'll get to all of these coming up, but yeah. I wear a lot of hats. And yeah, so past projects, these are these are my roots. So typical cognitive neuroscience focusing on attention processes. And recently I moved away from that purely basic science approach, just because I spent a lot of time in the research realm, but I saw a lack of will for innovation, and I saw data science, computer science being a lot of what was lacking. People had the will to innovate, but not to branch out into other fields. And so, yeah, to me, comp sci is as foundational to cognitive neuroscience as is an understanding of the human brain. But yeah, during this time, I worked with Raspberry Pis, MCUs, VR, and then I started with MATLAB, and then near the end moved to Python. And so just before I go into any particular projects, I'm just going to go over what is typical cognitive neuroscience. So it involves recording brain activity, and in most of these projects, that's electroencephalography, or EEG. Basically, you're just getting a voltage, a point voltage over time, typically from a lot of different sensors on the head. And so you can get a sense of activity of the brain at a high sampling rate. And then you present some stimulus, so it could be tones, auditory, visual, or even tactile. And then you embed triggers in the brain data stream that coincide with that stimulus. And then you analyze events in aggregate. So the brain is doing a lot of things all the time. So in order to get a signal from a particular event, you got to have that event happen a lot of times, and then average over that. And then EEG itself, so we're recording on the scale of millionths of volts, and averaging over time. And then we correlate the resultant waveforms to different behavior. And so when I started out, that looked like putting on neuroimaging caps, EEG caps, and bringing what's typically done inside outside. So having participants ride a bike and then having them engage with an auditory task. So they're responding to different tones and withholding response to other tones. And so we got them to ride a bike in either a park or beside a busy road. And so this is just an example of what the data might look like. Particulars don't matter too much, but this is a good example of what the data looks like. So you have average waveforms. So each of these is from potentially hundreds of trials. And then we look at different characteristics of those aggregate waveforms and looking at the difference to the stimulus across conditions. And then I moved into working with EEG in the context of virtual reality. So instead of going outside, instead bringing complex environments inside. And so VR allowed precise control over complex environments. And interestingly, allowing us to isolate attention in depth. And so this is just an example of the first study I did with VR, is just validating that it's comparable between just a typical task presentation. But VR kind of opened up some new questions, some of which involve how are we processing depth. So in this paradigm, we had size match stimulus. So if the participant was over here and looking this way, the orbs would be in the exact same position and have the exact same size. And the only difference would be how they have to converge or diverge their eyes. And yeah, this is a lot. This is just another example of what the data might look like. So creating heat plots of activity in different time windows. So we're talking on the scale of like milliseconds after stimulus is presented. Yeah, and just comparing and contrasting different conditions. And so yeah, this is what I moved away from, is just making plots months later after recording a bunch of data. Yeah, so understanding this in particular isn't too important. Yeah, so that was typical cognitive neuroscience. And now I'm going to intro some of the more what I think are approachable projects. So in this time frame, I've expanded to using eye tracking, different types of neuroimaging, web development, machine learning, and as Hannah said, first crack at commercialization. And so I'm just starting with a broad overview of what BCIs are, brain-computer interfaces. And so there's data science involved at every stage. And so that looks like acquisition. So we're getting the data, we're reading the brain in some capacity. And so again, that's just recording this data. And then I guess this is probably the most data sciencey part, where you then, once you have the data, you analyze and interpret, and often along with the brain data, some behavioral data as well, like how people are responding, potentially what are they looking at. And so you can use anything from basic thresholding to constructing a complex hierarchy ML model. And then the output being that it's a brain-computer interface, so we're relaying that information back to the user in some fashion. And so that could be as simple as turning on an on-off switch. It could also be controlling prosthesis, so an arm for like amputees, or a wheelchair. But in my opinion, those aren't the best use cases for at least EEG or low fidelity neuroimaging. And so by that, I mean, controlling stuff in the physical world isn't the most effective if you don't have something embedded in your brain. So like Neuralink, which is not something I'm currently doing. But to that end, the next projects I'm going over are more fixated on using BCIs to guide human behavior rather than moving physical objects. And so the first one, we have my project called Koala Academy. So we have a little koala mascot. And this is, a web browser-based EEG accelerated language learning platform. So we have neuro-guided learning, so using real-time brain activity to support the learning of Mandarin. Then we mixed in some flashy components like gamified content and leaderboards. You can see how you're comparing to other users. And then this one is currently part of a validation study at the U of A. Yeah, so this project, I'm going to go fairly into detail. So if something doesn't make sense, feel free to put your hand up and I can explain further. But yeah, Koala Academy, how do? So basically, where does data come in this? At every stage, it's pretty much all data. So in the baseline, we get the user's brain data when they are learning words and while they're being tested on whether they learn those words correctly. And next, we create an individualized model of the user's brain activity from that baseline data. And then we use that model to change the stimulus as per the predictions of our model. And the predictions being whether we think they're going to learn the word association or remember it at a later point in time or not remember it. And so a given trial of this during the baseline, you would first study it and we would record your brain data and your response. And then at a later time point, again, this is still in the baseline, we would test you on your ability to remember that association. And so this one was, this is a true association, and now this one is an incorrect association. So they responded that it's incorrect, meaning they got it correct. And so we can now tie this response back to the initial brain data that we got, if that makes sense. So basically this is our data and this is our label for it. And then from there, we create a model derived from a bunch of those snippets of brain data that are time locked to the presentation of the word associations. And then each of those have a corresponding label of whether at the study phase that was correctly recalled or incorrectly. And thereby creating a model in which we can get a binary output of yes or no, or a gradient output as to whether the input of brain data is likely to result in remembering. So then we can use this model in real time, and then we can change the stimulus that we're presenting the users, thereby avoiding going back to associations that we predict them to remember highly, and then focus more on the ones that they conversely we predict they will not remember. I think I actually have a little. Here we go. Okay. Yeah, so this is just a brief overview, kind of restating what the flow of things, but in a more flowchart fashion. I speak in flowchart, so this is my natural. So we have multiple user pages, one for the baseline, one for the session. We have some Google authentication. We have the user do a baseline. So we initialize all the different trials, and then we get them to learn a pair association, and then we get them to, we test them at a later point on that association. And then upon saving those, basically just a CSV of brain data with the labels, we turn on a GCP, Google Cloud Platform compute engine, which then loads in the data and constructs a model, which we then use in our session. And so we load in that model, and we get a classification of live brain data and modify subsequent trials. And then you can save the data and look at aggregate information in the profile page. All right. Yeah, I guess I'll stop for questions. Any questions thus far?
Hey, Eden, this is Shan. I have a question about the constraints. What kind of constraint you've used during the training, like by manpower or by other features or label functions to like say the horse is correct, but mother is incorrect?
Sorry, the constraints?
Yeah, like how to let the model know like the label is correct or not.
So during the baseline, all of the studies associations are correct.
Mm-hmm.
And so they just have to basically start the trial looking at the association, and then respond correctly, which is always going to be correct. And then the test is, it can be either presented as an incorrect or a correct pair association.
Mm-hmm.
Does that help answer your question for constraints?
Yeah, but further consideration is, what if like the test result is false? So how do you deal with that situation?
Really, we just break it down into, did they get it correct or incorrect as
Mm-hmm.
like the end result of the label. We don't break it down into like, is it a hit? Is it a miss? Is it a correct reject? Like,
okay.
Because yeah, there can be 4 outcomes from that, but we just binarize it.
Okay, yeah, thank you.
Yep.
I see a question in the chat here from Ben. I'm wondering how much more effective this method of language learning was compared to traditional methods. Did the effectiveness vary from person to person?
Good question. I would very much predict that it does. Currently in early stages of validation, so I don't have a strong supported answer to that question, but feel free to follow along, and we will be publishing our research outcomes. I guess also to that point, we're creating a model specifically for each user, so we don't have like a generalizable model that we use like transfer learning. It's like all generated specific to the user. And so potentially down the road, using a different architecture in our model would be more useful. All right, I'm gonna go on. So next, this is just a one slider. This is the newest project I have ongoing. It's open stroke rehab. It shares some similarities to Koala Academy in that we get a baseline and create a model. But in this case, it's not predicting learning. It's rather predicting someone's intention to move. So we would have the user go through a bunch of baseline trials, basically saying, imagine moving one of your arms or a specific arm. And so the intention of this program is to provide open source, open access stroke rehab. And so we would then, after the baseline, in the session, be classifying the intention to move a given limb. And then, as with stroke, you often have impairments in the ability to control or engage muscles. And so our prediction of their intention to move would then result in stimulation of the muscles. So this is TENS or cutaneous electrical nerve stimulation. And then we would similarly pass an electrical current through their brain. Yeah, this one's a fairly early stage, so mostly just throwing shit at the wall. But yeah, it's kind of the exciting stage, in my opinion. Yeah, and then our intention is to have it open sourced and relatively easy to use as far as setup. I think we're eventually hoping to have it compiled as a Windows application. But yeah, it's a fun one, being as we have to have fairly synchronized hardware as far as the TENS unit and the TDCS. Any questions on this one?
So I have a question. How do you, based on the EEG signal, how do you classify which limb the patient is intending to move?
That's a good question. We are in still the early stages of that. We're kind of, so there's a device called OpenBCI, or a suite of devices, and I think I actually have a picture here. Yeah, so this has up to 16 recording channels, but the mapping of the different motor movements and how it's represented in the brain is reasonably small area in the prefrontal cortex. So we're basically going to cluster a bunch of electrodes around that area, and then we're thinking with enough density and a well-spaced reference electrode, we'll be able to differentiate like coarse movements. So we might not be able to get, we're definitely not going to be able to get like exact finger movements. But yeah, we're working towards having like very general movements.
Thank you.
And I think it would be, once the system is in place, finding those limitations would be fairly easy, as far as just asking them to imagine moving different elements, different digits or limbs in the baseline, and then seeing what accuracy comes from that in the actual session.
So that's basically how you're gonna create your training labels, by testing each patient's baselines.
Yep, we'll
asking
just
for-
we'll be recording EEG, and then we'll just prompt them with imagine moving X part of your body, and with enough samples, yeah, hope is we can, with the clustering of electrodes around that area of the brain, external the scalp, we can get some differentiation of intention.
Okay, yeah, thank you.
Yeah, there's some fun challenges with that, considerations as far as the physical hardware. So this is an open source project in itself, as far as we have the 3D file, and so we're going to be modding this file to have these rigid electrodes clustered in that one area, but also still structurally sound. And I have a bunch of them, so they're pretty strong. Any other questions on this one? All right. So next, it was originally akin to the open stroke rehab, and for the longest time it was just throwing shit at the wall. But the overarching goal is to combine eye tracking, EEG, and body tracking into one streamlined user interface. And so that is also open source. And our goal is to be able to do this for under $1,000 and have it be research grade. And so we use distributed hardware accelerated machine learning. So we have a Raspberry Pi wired up to a TPU, Coral Dev board. And then we have a stereo camera module to get 3D points in a given experiment space. And then we have eye tracking with a POV camera, and then a camera looking at the eye. So we're able to construct a 3D gaze vector. And then we also have an in-house EEG, basically biosignal acquisition board, similar to OpenBCI, but they just raised our prices. So we've had to go in-house to meet our under $1,000 goal. And yeah, this is where I like being at, a good balance of hardware and software, something that could be used for research, and is just generally a bunch of hard problems all combined into one really challenging thing. Just makes it all the more fun to work on. And as far as like where data science comes in here, although this project's heavily rooted in hardware, I'd say the majority of innovation comes from the software side, in actually synchronizing those data streams, even just like saving them in a synchronized fashion, but visualizing. So we have to bring all this data into one unified space, and creating like a user interface that's actually useful. And so I think right now we're using VisPy widgets in a PyQt5 frame. Yeah, lots of fun stuff. And so that's also hardware accelerated, GPU accelerated graphics. Any questions on this piece?
Yeah, this is Shang again. Like, I'd like to ask a question about the hardware, like the Raspberry Pi. So how large RAM does that Raspberry Pi have?
I just like to get the max. I imagine it's probably, so we can get basically live classification theoretically up to 20 times a second in our current rig. We're shifting from wireless between the Pi to the Coral dev board to a wired connection.
Okay. Yeah, because I'm thinking about this Raspberry Pi needs to like use machine learning models, so it needs like a large RAM to run it.
Yeah, so that's all boarded to the Coral dev board. So that's what's running the body point classifier.
Awesome. Yeah, thank you.
Yeah, so we run that independently on both images. Wait, no, we combine it into one image and then classify the points, all the points on the separate entities. And then I believe we compute the 3D points on the Pi itself. Cool. So that processing happens locally on the Pi.
Yeah, that makes sense. Because previously my colleague used like only 8 GB for running, playing the arcade only. So for machine learning, I need to like way larger. Yeah, thank you.
Yep. Yeah, I'd recommend this setup, and we're just working on our documentation now. So if you have specific questions down the road, would be happy to help. All right. And no other questions on this piece? All right. Next is RemBRAINdt. And so it's very broadly generating brain-derived art in a brand new neuro entertainment industry. Because at least in Canada, we don't see any competitors currently on the market or on the horizon. But essentially, users can put on physical EEG hardware at public or private events. They can constrain the creation of brain-derived art. So we have generative algorithms in JavaScript that are both constrained by an emotional classifier as well as the customizations the user input at the beginning of the session. And then it's web-based as well. So we're working on having it for use at home for anybody who has hardware. And we're looking at expanding the hardware that people can use on the platform. So there are some fairly popular and widespread EEG devices. And so we're looking to piggyback off of that hardware-driven market. And yeah, it's been I guess we've only been going for about a year. It feels like a lot longer, probably because like COVID. This was actually just some like offhand idea I had last spring or summer, but we ended up winning a international Neurotech competition. I think it's called the Neurotech Cup, which is hosted in Russia, and we got a People's Choice Award. I wouldn't say we won it. There's a lot of other really cool projects that went above and beyond. But yeah, now we're like solidly in our first attempt at commercializing. Actually had a launch planned tomorrow at Beakerhead, but that was unfortunately messed up due to COVID. But yeah, we'll be out and about in Calgary and Edmonton definitely next spring. So come check us out. Yeah, and so this has been a lot of like learning on the business side, and then project management as far as coordinating people, making sure developers are engaged, getting funding. So yeah, some more like the logistics side of project management. Any questions on this piece? All right, moving on. So trends in neurotech. So if you're looking at Alberta, NeurAlbertaTech's kind of the trend. So we are like the prominent organization that's trying to network people together, provide professional development. So yeah, lots of workshops. We have workshops starting on Monday, which is a 1 hour a week for 10 weeks workshop, where you actually can do anything from building an EEG circuit in your home to learning to program your own BCI or getting equipped with the skills to do so. And then we hosted Canada's first brain-computer interface hackathon coming up on 2 months ago, which is really cool. Yeah, and then we support internal project teams like the ones I mentioned, but also external. So we have several project teams from the hackathon that we're supporting as they develop further. And so what is NeurAlbertaTech? Basically, we combine the strong neuroscience landscape, which is surprisingly strong in Alberta. There's like nationally renowned groups at the U of A, U of C, and U of L. And then we connect them with engineering and ML researchers, which are internationally renowned, and yeah, connect them with the startup community, which is actually fairly well established in Alberta. Yeah, and lots of different ways to get involved. We're currently setting up a University of Calgary student chapter. So if you're in Calgary, you can look forward to that. They're going to offer a lot of the same things on a smaller scale. Yeah, and so if you ever do anything neurotech related, this is kind of our gimmick, supporting from just ideating with other experts all the way to scaling. And I think that's the end of my presentation.
All right, thanks a lot, Eden, for this very insightful and wholesome, I would say, presentation. You've touched down, like the basics of neuroscience, and then how you applied technology in this space, and all of the projects that you touched on. I think there were four of them. They all had their very interesting and impactful, very promising future too. So now I think I can open the floor for any questions, if there are any. Okay, if there's no questions, I have a question. If people from the IntelNova solutions community is interested in any of this project, how can we get involved?
Good question. Definitely not planted at all. So the NeurAlbertaTech Neurotechnologies Limited is the non-profit organization that's kind of the large body at the top of NeurAlbertaTech, and from there we have ongoing multi-year projects, and so we take on people fairly consistently from comp sci and engineering pretty much all the time. So yeah, if you're looking to join a project team, level up your skills, and really it's the skills we try to help people develop in the workshops are very readily transferable to any data science. And then, of course, next year we'll have the hackathon as well, which I think we gave out, or giving out $10,000 in prizes. So it's a fun time. Got pretty sleep deprived this year.
Okay, thank you, Eden. And thanks everybody for joining. I think both the Slack link and the website link for IntelNova Solutions is in the chat, and in the future we'll be bringing more of these industry experts to our workshops, and we're hoping also to maybe, like Eden, as we talked about before, if there are chances for collaboration and bringing projects within IntelNova Solutions, we can also basically network with these industry specific domain experts, and then bring you any projects that you might be interested in. So just leave us a comment in the Slack channel, or just basically anything on your mind. Let us know, and we will try to bring the best experience for everybody in this group. Thanks a lot. And if there are no other questions, I would propose us to give Eden another round of virtual applause. Thank you, Eden, and thanks everybody.
Thanks, Hannah.
Thanks.